Higher Mathematics, Notes and Examples. This is lesson 4, Inverse Functions. We'll start thinking about this topic by looking at a very simple function, and that function is f of x equals 2x. So we're doubling each element in the domain to produce an element in the range. F of 5 would be 2 times 5, that's 10. F of minus 5 would be minus 10. We can see that f of 0 would be just 2 times 0, or 0. In fact, for this function, each and every element in the domain is mapping to just one element in the range. And that means that this kind of function is a one-to-one correspondence. If we have a one-to-one correspondence between two sets, the domain and the range, then we can ask the question, is it possible to reverse this process, to reverse this function? And the question is there a function, and we'll call that f to the minus 1 of x, which would be an inverse function. Now, what might be a function to reverse doubling? You might, of course, see that the answer is dividing by 2. So the inverse of f of x equals 2x would actually be the function f of x equals a half x. I'm going to look at this topic at how we can find that inverse function using a very simple technique. If we have a function which is not a one-to-one correspondence, for example here a many-to-one function, f of x equals x squared, then we have a problem when we try to find the inverse. So if we think about f of x equals x squared, we know that if you square the positive values on the x-axis, you can get the same answer as you would if you squared the negative values. For example, 2 squared would be 4, and also negative 2 squared would be 4. So you can see there is a problem if we try to find an inverse function, or if we try to reverse that process, because if we do so, then given the value 4, which value do we go back to? Is it negative 2 or is it 2? So we say that no inverse would exist for this particular function because it's not one-to-one, and we wouldn't in this course be asking you to find the inverse of a function unless it was a one-to-one correspondence. It is worth pointing out, however, that we could restrict the domain of this function. We know that we're able to do that if we were to put down a condition on the values of x. And we can see here actually that if we were to say that f of x equals x squared, where x is greater than or equal to 0, then we remove the negative values and suddenly this function would be a one-to-one correspondence. And then there would be an inverse to the function x squared, and that would be f to the minus 1 of x, which equals the square root of x. In this topic, however, we'll stick to functions where we can find the inverse, and there's a very simple process that we're going to use. So this is the method that we're going to use, and it's important that you make sure you have a note of these steps, and that in the examples today, you think about each step as we go through the process. First step would be that we write the function not with f of x, but with y, so it would be y equals. We then make the letter x the subject of the expression, so we use algebraic manipulation. You'll be familiar with changing the subject of a formula. When we have x as a subject, we have x on the left and a formula on the right. We then switch x and y, so we interchange x and y, and this would actually now be the inverse function. So we can express that as f to the minus 1 of x. This seems a little confusing at first, but when you see a few examples and you get some practice, you'll see that it's actually quite straightforward. So let's look at some examples of how to do this in practice. So in our first example, we have to find the inverse of the function f of x equals 3x minus 7, where x is a member of the real set of numbers. So we remember that our first step is to express the function as y equals 3x minus 7. And then we're going to rearrange so that x is the subject of the equation. So we'll do that by switching the sides here. So we have 3x minus 7 equals y. And then we want to add 7 to both sides of the equation. And we divide by 3. And actually, having done that, we now have the inverse function. This is the function that will take you from a value in the range to a value in the domain. So x is our domain value. So really we want to express this then as the inverse function by switching the x and the y. But we do that by writing down that we have f to the minus 1x. So we really express the function in terms of x again. F to the minus 1 of x equals x plus 7 over 3. This is our inverse function. And again, x is a member of the real set of numbers. Okay, in this example, we're looking at a function q of x equals x squared minus 1. We're given a domain that x is greater than or equal to 0, and other than that, it's a real number. So, step 1, we have a function, q of x equals x squared minus 1. Our first step, of course, is to express that as y equals. So y equals x squared minus 1. We now want to rearrange the formula so that x is the subject. So we'll do that fairly easily by adding 1 to both sides and then taking the square root. So the x equals the square root of y plus 1. And this is our inverse function. So we would interchange the x and y, or we can simply say now that q to the minus 1 of x, the inverse function, would be the square root of, and remember it has to be x in here, square root of x plus 1. And we need to put a little restriction on the domain of this inverse function because we know that we cannot square root a negative. So x is really going to have to be greater than or equal to negative 1. Apart from that, any real number will be acceptable. So that example is worth studying. You may want to rewind the video or pause the video and think about some of those steps. Okay, example 3, we have two functions, f of x and g of x, and we're asked to find a composite function, h of x, and then state the connection between f and g. This is an important example that covers a very common idea in this particular topic. So let's find h of x. That will be g of f of x, and we should be familiar now with how to find a composite function fairly easily. So we're going to find g of 5 minus 4x, and if we do that, then we're going to find that we have 5 minus 4x in brackets, all divided by 4. And we will find that the answer this time is actually just 4x divided by 4, which of course is x. So we have actually the identity function, and the identity function is the function h of x equals x or y equals x. Really it's just a function that gives out what you put in. So for example, if you find h of 5, then you get out the answer 5. This is really important. This tells me that there is a connection between these two functions. It's that they are the inverse of each other. So it's really important that we notice that if f of g of x or g of f of x, so if either of these two, so in this case we started with g of f of x, if g of f of x is equal to x, or if f of g of x equals x, in fact they'll be the same in this particular example, if they equal x, that tells us that this pair of functions are mutually inverse. So let's write that down. F and g are mutually inverse. And this is an exception to the general rule that f of g of x and g of f of x are usually not the same. Well, they will be in this case. They'll both equal x. Finally, a way to write that would be to say that f of x is equal to g to the minus 1 of x, the inverse function for g. And of course we could also write that g of x equals f to the minus 1 of x. So that's another way to say the same thing. Important that we're aware of this, as it does occasionally come up in the exam, and it's all about the composite function providing the answer x. As always, it's now over to you, and it's time to get some practice. Here are the pages from TJ or Heinemann that would be useful for you to attempt exercise questions from. This has been lesson 4 of 4 on functions and graphs. I look forward to seeing you in our next video on a future higher maths topic. Until then, take it easy.